Friends, I'd be introducing you to this concept of what is known as a well to wheel analysis. In brief, we can call it as WTW. So, W stand for well and to wheel analysis. Now, this is a jargon in the sense that it is a word which would be describing the analysis of carbon footprint calculations, considering even the material which has gone into the exploration of the energy source. Could be petrol in case of petrol engines, a petrol vehicle, or could be a battery in case of a battery driven electric vehicle. So the concept is we need to in toto do the carbon footprint calculations. So this wheel to well analysis, I'd be explaining you with an example of popular EV in the market, in the Indian market, that is Tata Nexon, and a similar vehicle, the petrol variant of it, you would be taking for comparison. The specifications which I would be using, they are a bit year older. So what matters is not the values. What would matter is the methodology which we should understand in this well-to-wheel analysis. Now, when I'm talking about this well-to-wheel analysis, I have in my slide written these two terms, WTT and TTW. So I will be often using this three terms. So we need to be clear on what exactly they are and how are they different. So let me just again revise what we mean by WTW. So WTW would be well to wheel analysis. WTT would mean well to tank analysis, and TTW would be tank to wheel analysis. Okay, so now what is a wheel and what is well, that we need to be clear before we start the analysis. So when we talk about wheel, what we refer to is the on road driving of the vehicle. So as the vehicle moves and it traverses some kilometers, what would be the energy consumption and what would be the carbon footprint generated? So that is what we mean by wheel. And by well, if it is a petrol vehicle, we would start the analysis from the exploration of petrol in the refineries. And if it is an electric vehicle, we would start with the battery stuff. Uh, in the life cycle analysis, or what is also known as cradle to grave analysis, we also consider the other parameters like what exactly happens, how the batteries would be disposed, like, or how the materials of the car would be disposed, whether some of them could be reused and the stuff like that. Okay, so we will not be doing that level of analysis in the well to wheel analysis. We would stick to only some very basic and fundamental aspects like how much energy goes into the battery in case of battery vehicle, and how much energy goes in charging the battery again in the electric vehicle. When we talk about petrol vehicle, we would go into how much energy goes in exploring the petrol or and as also refining it, and how much energy is used by the car for some kilometers of travel. So we would be expressing it as per kilometer travel and stuff like that. Let me start with the analysis now. As I said, I'd be using this model, Tata Nexon long variant model of EV, and that model, I'm having these specifications in mind. So what is important for us is to understand that this model has a battery of a capacity 40.5 kilowatt hours, right? So this would be very relevant for us in our calculations. This is the most important part. Other things you must know, though it might not directly come into the analysis part, but we must be pretty sure that this finally the vehicle performance would depend upon the motor which is being employed and the motor characteristics. Okay, right. So there's Tata Nexon variant, which I'm talking about. It uses PMSM, namely the permanent magnet synchronous motor of capacity of around 106 kilowatts. Okay, it generates a torque of about 215 Newton meters. It's a front wheel drive which we'll be considering for analysis. As I said, the battery specifications are more important because these values, the values of energy which goes into the production of battery would depend upon what chemistry we are talking about. So we would be talking about lithium ion battery whose typical weight is about 300 kgs, right? And it is going to provide us about 135 watt hours of energy per kg of its weight, right? So this gives, in a way, the range of the indirectly, not directly, but the range of the vehicle. This stuff is important from the consumer angle as to how much energy goes into it, but it is also relevant to understand uh, and also to assume the losses which you'd be doing in the charging and discharging of the battery. Okay. Life of the battery is important because finally, when we are talking about uh, per kilometer, and when you are talking expressing every carbon footprint per kilometer, how much the battery lasts and how much kilometers it is it is it has to be replaced, that would matter when we want to do the calculations of the carbon footprint. Okay, so here we are assuming a carbon battery life of about 2 lakh kilometers, right? Which is around 1500 full cycles. Uh, so here are some calculations. As I said, we were talking about a battery of capacity 40.5 kilowatt hours, right? And when you want to have this battery, uh, I looked into the numbers as to how much is the emissions when you manufacture the battery. For looking into these numbers, there are very interesting papers, but the paper which I had referred to, recent paper, gave me this figure. Uh, broadly, about 40% would go into the raw material extraction, the energy required, right? And hence the emissions from that. Then there is a cell manufacturing part. The cells which are manufactured, they are assembled, and then finally they need to be transported. Okay, you know that it's all quite geographical spread for all this. We get critical minerals from China, the refining also we could get it done in China. There could be plants located at different parts of the world, right? So those logistics and transportation are to be accounted for when we do this emission calculations, and obviously they would vary uh, depending upon the place where we manufacture. If you manufacture the battery at a place where the electricity comes from a cleaner source, renewables, this number would be less. Okay, so this numbers 90 kgs. How I got is I took this total total emission about 3700, and I divided by 40.5. Okay, so this gives us some pretty good number, about 90 kgs of CO2 per kWh of battery which is being manufactured. Okay, so as I said, when we talk about these specific numbers or we talk about this total number, we need to then convert it into per kilometer, right? And for that, not only the battery capacity is important, uh, equally important is how much is the battery lifetime. So as we had earlier said that we are assuming a battery lifetime of about 2 lakh kilometers, and if we divide this two, that is this total emissions upon this total life kilometers over the lifetime, we get to know this specific energy consumption and the specific carbon footprint which goes into the battery manufacturing aspect. So this would be considered in our analysis, TWT analysis. Okay. So now, what is more crucial in case of EVs is not this number. Okay, as we'll be looking into the comparison in the tank to well analysis, this number would be pretty small as compared to what goes per kilometer when you do the analysis of the energy which goes into the charging of the battery and its discharge while the vehicle travels. Okay, so that would be more crucial as you'd understand. And how is that calculation done? So for that, I had assumed the range. You know that range is basically the kilometers which the vehicle travel, right, per charging. So again, these numbers, these assumptions, we had used the data of Tata Nexon EV, and depending upon the kind of road one is traveling, this number could be less or more, right? We would get a better mileage. It's mileage in a way if you have a highway driving and steady driving, but if you have uneven terrain, this number would be lower, right? So taking this real world range as 300 kilometers, our battery consumption or the energy consumption per kilometer would be this. So how do I get this? So I had assumed that this 40.5 kWh battery, we can use about 38 kWh, and this 38 kWh would give me a travel of 300 kilometers. Okay, so this, if you divide, you get approximately this number. Okay, so this is the energy the battery would drain for every kilometer of travel. Every kilometer of travel. Okay, and then how much energy I need to provide or how much energy I need to put into the battery for that every kilometer. It would be more, considering that there are losses in the charging phenomena and also there are losses when the electricity is transported to the grid. Okay, so these numbers we can assume again, make a good assumption. With these assumptions, my 12% is the charging losses, 15% of the grid losses. I get this converted to a slightly higher figure. So it's not 0.127 kWh, which is required per kilometer. It would be slightly more considering the losses, and that slightly more figure in my case comes out to be around 1.14 kWh every kilometer of travel. Now mind well that this 0.14 kWh per kilometer, if it is generated from renewables, right, the carbon footprint would be zero. But if it is coming from the fossil fuel, then, and if entirely comes from the fossil fuel, the carbon footprint would be much more, right? So in the case like a country like India, where we get some of the energy or most of the energy from the coal-based power plant, right, and also from the fact that we are slowly moving towards renewable, these numbers are to be chosen carefully. So I had chosen a number of 0.82 kgs of CO2 per kWh. This calculation should be clear to you if you have understood the calculations which we had earlier done in our carbon footprint calculations course. Okay, so 0.82 kgs of CO2 per kWh is the value which I am assuming for the India's grid. As I said, if you consider France, where most of the energy comes from nuclear, this value would be pretty low. Or from Germany, where again some 40% would be coming from solar, this would be a lower value, right? So this parameter would vary from the country to country. For the present Indian case, we can take it as 0.82 kgs of CO2 per kWh. So now you have this mileage in a way of Tata Nexon, and we have this number from this value 0.2. How it comes is how much energy has to be supplied from the grid. Okay, so 0.14 was how much energy is required for the battery and how much energy has to be supplied from the grid. Okay, or how much stuff has to be supplied from the grid, that would depend upon the net efficiency, right? So this is point 1, 0.7, where we are considering the transmission and distribution losses, okay, and the charging inefficiencies. Now you might say that I'd already considered this here, right? So this I have considered at the at this household level, okay, household level from the DP to the house, right? Whereas this I have considered as a total grid level, which I am doing the analysis of the entire transmission and distribution networks. So from the power plant up to the DP, this all these values would reflect to 70%. With this 70% efficiency, right, that is 30% losses, my energy drawn from the grid would be much more, which is zero point 0.2 kilowatt hours per kilometer. Okay, again, these values would differ from place to place. If the efficiency is much more, the values would be less. If the losses and the theft is more, the value would be much lower, right? So the now the parameter comes to zero point 0.2 kWh per kilometer is the energy, right? This is the energy. How much is the carbon footprint? So for that, the specific energy value, specific carbon footprint value will matter. So the carbon footprint of generating 1 kWh of electricity, I'd assume it as 0.82, multiplying the two, you get 0.164 kgs of CO2 per kilometer of travel from the EV, right? So if this is clear, now your well to tank numbers are clear to you. Okay, so well to tank in case of battery vehicle, as I said, it would to be this number plus the number which we had got earlier, that is this number. Okay, so 0.018 kgs from battery manufacturing and 0.164 kgs of CO2, including the emissions from the power plant. Okay, these two we would get as the number for WTW. Now WTW is what? As in my jargon, as I said, it would include well to tank and it would include tank to wheel. Okay, so tank to wheel in case of EVs can be assumed to be zero, right? Because there are no tailpipe emissions. But whatever emissions are there, this thing from the battery and this thing from the charging of the battery, all this would be included in the WTW analysis. So in case of Tata Nexon, my number now with my assumptions, what we have got is the well to tank emissions are pretty high, 0.182 kgs per CO2 per kilometer, whereas the well to wheel emissions are zero. In total, which is well to wheel analysis, the total number for EV is 0.182 kgs of CO2 per kilometer. I hope it is clear to you. Right. Petrol, it is pretty simple. You already know this, how to do it. Uh, Again, I get some assumptions. I assume some numbers for petrol which is being extracted, and this is the number I have taken. Again, this number depends upon the where the refinery is located, what is the technology being used in the refinery, and the stuff like that. Uh, for me, this number is 0.33 kgs of CO2 per liter of petrol. Okay, now per liter of petrol has to be converted to per kilometer of travel, again by considering the mileage of the vehicle, which is Tata Nexon. Okay, this is what we do in the next slide. Okay, so as I said, well to tank analysis would include how much CO2 would be emitted per liter of petrol exploration, which would include extraction, refining, and transportation of crude oil. Okay, before it reaches the fuel station. So in this well to tank emission analysis, 0.33 kgs of CO2 per liter of petrol would be my number in your WTT. WTT means well to tank analysis. Now, in tank to wheel analysis, what is important for us is to understand the mileage of the vehicle. Okay. So, my numbers for Tata Nexon are 15 kilometers would be the mileage for every liter of petrol which is consumed by Tata Nexon. Okay, so the vehicle, petrol vehicle, I'm assuming that it is going to give me an average of 15 kilometers, right, for every 1 liter of petrol. And this number would come from the brake specific fuel consumption, or what is known as the brake thermal efficiency of the petrol car. Okay, so again, this parameter would depend upon the uh, quality of the fuel which you talk about, right? And sorry, this number will come from this BSFC and brake thermal efficiency. This mileage would come from that, and this would come from the in a ultimate analysis of your ultimate analysis of your petrol. Okay, assuming that it undergoes a complete combustion. Okay, so for me, this 2.3 kgs is the CO2 emitted per liter of the petrol, right? If 2.3 kgs of CO2 is emitted per liter of petrol, and if the mileage is 15 kilometers per liter, right? So that would give me a figure of, you per se, so 2.3, right, is the kg of CO2 per liter, and you are dividing it by 15 kilometers per liter. Okay, so you'll get how much is the kg of CO2 per kilometer. Okay, this is division, so this would be up, this would be down when you multiply, right? So you will have this as the unit. What is the unit? You'll have kgs of CO2 per kilometer as unit. So you need to divide this emission factor with the mileage to get the carbon footprint of the petrol car, right? So this is because of the tailpipe emissions, and hence we'll call it as tank to wheel analysis. Okay, so from the tank to wheel analysis for the petrol car Nexon, Tata Nexon, with the mileage assumed to be 15 kilometers per liter of petrol, we get a number of 0.153 kgs of CO2 being emitted every kilometer of travel. Okay, so adding the two means assuming this 0.153 and adding this 0.022, which comes from your petrol exploration. Okay, how this number has come? 0.022 would come from this. Okay, so this will give you this 0.022, considering the uh, life cycle emission per kilometer. It comes as 0.175 kgs of CO2 every kilometer. Now you see that these two numbers are pretty close. 0.175 and 0.82 are pretty close, and so in a way, both these W emissions of a petrol car and W vehicles of Tata Nexon EV, they are pretty closer. Why is this so? This is so because uh, India still uses pretty large quantity of coal, right? A large quantity of coal is used in its generation of electricity, which is being supplied from the power stations. As we move away from coal based power generation to renewables like solar PV and wind, this value would be much more favorable for EVs, right? So for EV, this value is going to come down substantially. For electric vehicles, this value is going to come down substantially if we move on a fast track towards renewables and we reduce our consumption of coal. Till then, we need to be very sure that uh, just promoting the electric vehicles without moving towards green electricity might actually uh, lead to more emissions if we do this analysis from the well to wheel. Okay, from well to wheel, if you analyze, then the shift towards EV without without actually reforming our grid or without actually greening our grid would no way help the environmental cause. Okay, so these are the insights which we get from the well to wheel analysis. Obviously, these numbers are going to be very sensitive to the assumptions which we are making, and that is why there is something called as sensitivity analysis which has to be done to account for, like for example, you can do the analysis, say that supposing in 10 years time the percentage of coal reduces from 70% to 50%, what would be the well to wheel analysis of petrol versus vis-a-vis the EV, right? Or you might say that supposing India adopts 10% of the nuclear along with 50% of renewable, so it comes to 60%. What now would be the well to wheel analysis? So everything would depend upon the scenario building, and that we actually do in what is known as sensitivity analysis. But as of now, we see that these figures are pretty close, well to wheel analysis, and from this analysis we can in a way conclude that pushing electric vehicles and subsidizing them is not going to give much more environmental benefit unless and until we fast track our shift from fossil fuel based economy to renewables. Thank you. Bye for now.